Okay, welcome back. What I want to do is to continue with IEE regulations. Okay, so let me just fill this in so that you know this is IEE regulations part 2. Let me see if I could have a little space here for myself and put it in, insert a text box. I'm going to put a text box here. Okay. Oh goodness me. Now you see, this is where it gets tricky because I'm trying to do two things at once. Okay. IEE regulation formulae or formula. Formulae, and this is part 2. Okay. Okay. Let me just go back, make sure I can get this all the way in. Okay. And let me just try and save that. Okay, I'm going to go to save as it is and see if that comes. No. Okay, cancel's not working the way I think, but I will look into it a little bit later when I'm not trying to do too many things all at once. Okay. What we have here is module 8, but ignore the module, they're only for a point of reference, symbols. Millivolt amps per meter, millivolt per ampere per meter, but same thing. Okay. Now, thermal insulation factors. Now, the thermal insulation factors refers to the temperature that a cable will endure when it is covered or run in a house or somewhere else, or in ducting or in trunking or in conduit, etc. The thermal insulation refers more specifically to housing where you've got loft insulation, and those cables are then covered over by the fiberglass insulation of the property, which can cause the cable to increase in heat, and that will then cause the insulation to break down, giving you a problem that you don't really want. So thermal insulation factors, now make sure you are up to date in regards to the IEE regulations in this matter, and look at the modern IEE regs at all point in time in case these numbers changes. In contact on one side only, okay, 0.75, completely surrounded by thermal insulation equals 0.5, okay. Okay, let me just come back. Now you will do this for yourself, you will carry out the calculations, and if you look at some of the videos I've done already, you'll find that I've done this for you previously. Tabulated current carrying capacity of cable equals IN over C1 times C2 times C3 in amperes, okay? Sorry, let me just take that off. This then tells you, going on to tell you where C1 equal correction factor for grouping, C2 equal correction factor for ambient temperature, C3 equals correction factor if cable is in contact with thermal insulation. Okay. Now when the overcurrent device is a BS3036 fuse, then the tabulated current carrying capacity of the cable will be, and here you have your changes which you will need to bear in mind at all times, and again confirm with your IE regulations for current standards at all times. Okay. IN over C1 times C2 times C3 times C4 in amperes, where C4 is 0.725. Okay. Now voltage drop must not exceed 2.5% of the nominal voltage when carrying full load current. Now we still work to this standard basically of 2.5%, 6 volts basically, I believe it will be referred to now. But make sure that you're familiar with the current voltage drop in any circumstances that the IEE regulations is employed to enforce and ensure that you've met that standard at all times. Okay. Maximum voltage drop equals voltage times 2.5 over 100. Okay. Actual voltage drop equals millivolt amp per meter times IB times length over 1000. Again, that is for you to remember what IB is. I don't. We looked at it earlier. Okay. Let me just get this into view. Okay. Let's not go too ahead of myself. Okay. Right. Now, module 9, again, just for point of reference, formulae, space factor, cross-sectional area equals pi times d squared over 4. And what is pi? Pi equals to 3.142 as a general rule, okay? A times 45 millimeters squared over 100 equals total cross-sectional area of cables, okay? Now, the space factor is relevant to what space is left in a trunking, conduit, cable tray, etc. to allow for heat dissipation of the cables. Okay. A equals 100 over 45 times total cross-sectional area of cables. He's just repeating what he said earlier, depending on what you're looking for to find. Okay. And here, where A equals the cross-sectional area of the trunking, that's CSA, okay? CSA means cross-sectional area. So it could be a 2-inch trunking, 3-inch trunking, 4-inch trunking, 6-inch trunking, etc. Depending on what it is. Let me just move this a little bit. I don't want when I get to come to look at it, look back at it, it's coming off the screen on the edge of the out of sight. Now, cross-sectional areas of protective conductors, S equals square root of I squared times T over K, millimeter squared. Now, again, you've been told what K is previously, so you need to look that up for yourself and become familiar in writing these formulas out, so you have an understanding in your own method and in your own learning profile. Okay. Where S is the cross-sectional area in millimeter square, I equals value of maximum flow current in amperes, T equals operating time of the device in seconds, K equals factor for specific protective conductors. Okay, now remember, the faster your operating device can operate, the safer your circuit should be, because if you do not have current, a large current flowing through your circuit for any length of time, it will make sure that it minimizes damage to the cables and its insulation. Let me make this a little bit bigger. I believe in making things big so it minimizes the stress of trying to read it. Okay, I don't like anything that gives me stress to read, so it's important that I apply the same thing. Now here you'll see the IE regulation 15th edition. We're no longer on the 15th edition, are we? We're now well into the 18th edition. Okay, so let's look at this. Let me put in a text here for now. Okay. The 18th edition. Okay. So this here So this here can be scratched out. Let me just see if I can put a highlight on it. Make this thicker. Okay, let me see if I can yes, okay. Let's see if it will work. 1 second. I'm just trying to see if I can cross this out. Okay. Yes, I can. Okay. Yes, I have. Okay. Out. Okay. Now make sure you are familiar with the 18th edition, and you now need to look that up in that sense. Okay. This is just, but the data and the formulation of these formulas are still relevant to this day. Okay, the formulas has not changed. They may be improved upon, other things may have been added to them, so that is what you need to be sure that you are looking at the correct regulations at all times. Now note in the information given, IB equals 45 amps, type of device equals BS1361, cartridge fuse, length of run equals 14 meters with 4 bends, ZE equals 0.4 ohms on TNS system, K for steel conduit equals 52. Okay. Determine rating of device, use table 8C. Okay, now be aware again, these tables may have changed, so they may be under a different name, but you're looking for the determining rating of device, so that the heading would be familiar. Okay, for this circuit, when IB equals 45 amps, IN equals 45 amps. Check IN is greater than IB. Yes, values equal at 45 amps. Okay. Let me just get myself in order and bring this back into play. Let me drop it down the size, okay, so we can see it. Okay. Current carrying capacity IZ equals 55 amps and volt drop equals 4.2 millivolts amps per meter. Check IZ is better than IN, and it is. Okay. Again, this is for you to do your own calculations. I won't be doing the calculations for you. You have to make sure, because you're going to be required to calculate this probably on the job or in your own examination in your course. Voltage drop, permissible voltage drop, 2.5 volts. Sorry, my apologies. Voltage drop, permissible volt drop is 2.5%. Times 240 equals 6 volts, okay? Volt drop to cooker control unit. Voltage drop for cable times IB times length over 1000, 4.2 times 45 times 14 over 1000 is 2.65 volts. Okay? And again, you will need to confirm that the voltage here that I've got here is correct. That's for you to do. I'm not going to do it all for you. You cannot just sit there and do nothing or think you can learn all of this from the screen. That will not work. That is not the case. It does not work that way. You have to do some graph yourself. Right here we have to determine conduit length, conduit size, determine conduit size. Okay, let me just bring this over a little bit. Okay, now here we have a length of, I don't want to go too far up, length of run. Okay, and it's telling you the length of run overall. Okay, length of run equals 14 meters. You need to count that up, make sure it is 14 meters. You have to do some little bit of work. Number of bends, how many bends do you see? 4. Well, it says here 4 bends. Okay, note table 12D is limited to a 10 meter length of run and to 2.5 meters for runs incorporating 4 bends. Now this may have changed, so look at it. All I'm trying to do here is to provide you with knowledge that you may be able to apply in today's world, applying the updated relevance and IEE regulations, but the principle of how it is implemented still remains the same. Choice then is either to have the run and consider conduit in 2 sections with intermediate draw in box, or carry out calculation using space factor formula. Method A preferred since there are fewer calculations and easier since conduit run repeats itself with 2 times 90 degrees bend at each end. Take length equals 7 meters. Again, be sure that you're looking at the right tables. These tables may have changed. 12C factor for 10 meters square equals 105. For 2 conductors equals 210. Now again, they may have changed because I believe that, as you know, we were in the European market, but we've left Brexit sorted out. So that's again, the IE regulation may have been amended to take into account all situation. Okay. And here you have the conduit size selected, 25 millimeter. I'm just dropping down a little bit by a notch. Okay. Right, and max Z is the maximum total earth fault loop impedance and can be obtained from table 41A. 41A1, page 26, which will now bear in mind the page may not be the same, but you're looking for the max ZS, okay, which that will still be applicable. ZS will still be applicable and will still be in today's relevance. It is a consistent, okay, which will give a disconnection time within 0.4 seconds to the socket outlet final circuit in the cooker control unit. From table 41A1, max ZS value equals 0.6 ohms. Calculate actual ZS value. Use equation ZS equals ZE plus R1 plus R2. ZE equals 0.4 ohms on TNS system. From table 8D. Now again, be aware that these tables may change, okay? And you need to keep that in mind. But I'm providing you with a information that you can apply for yourself to show you how it is done, okay? So I would recommend you need to write these out so you know, and look at your on-site guide. Use the on-site guide because it tells you exactly what you need to be doing. I think I'll need a little bit of lunch. I think I'm going to have to look into that. Right, from BS4568 data, the resistance of steel conduit. Okay. Now you may look at this in a different way because we are using more plastic conduit now than we did before. Okay, but in certain circumstances, plastic does not offer the same protection as steel does. To bear that in mind. I don't need to go over this with you. You can do this for yourselves, okay? But for current IF, voltage over ZS, okay? And that's for you to look at in your own time, okay? Now let me just move this a little bit. Make sure that is in view, yes? If you want to determine the cross-sectional area of a CPC, circuit protective conductor, the circuit has to be checked against the thermal constraints using formula S equals etc. square root of I squared times T over K. Okay? And I'm not going to go any further than that. That is for you to do yourselves now. Okay? Summary of answers, okay? And that will do. And before we go any further, I'm going to stop there for now, okay? And I will continue with this on in part 3. Assignment B, okay? No information given, here's etc. And then you will look at calculating these things for yourselves. Okay, thank you for your time. I'm hoping that you will find this useful. Have a good day. Bye, and I will see you in part 3. Bye-bye.